Okay, here's a problem that has to do with sound. It says that there's a 75 centimeter long organ tube which is open at both ends. I've started the drawing for you. This is 12-3, and I've started the drawing. This is the pipe, and I've shown it in 3 different situations. The first situation is what's called the fundamental. And in the fundamental, what happens is there's a standing wave setup. The standing wave has to have an antinode at this end because it's open, an antinode at that end. So here's what the wave has to look like. That is, in this case, what happens is that the wavelength of the fundamental, lambda 0, is related to the length of the tube. How? Well, you can get half of a wave in there. So therefore, it takes 2 L's, 2 lengths of the tube, in order to get the first fundamental wavelength. Okay, this is the next one, first overtone, lambda 1. Here, when you set up the standing waves, antinode at this end, antinode at that end, then it turns out that you have exactly 1 wavelength in L. And so if this would be lambda 1 is L. But humor me for a minute, I'm going to call this 2L over 2. Same thing, right? But you'll see a pattern that develops. Here's the next one. In this case, antinode at this end. Then, rest of the wave, antinode at the other end. And so in this case, lambda 2 is 2/3 of L. So this is 2L over 3. This helps you to see the pattern, I think. It's 2L over 1, 2L over 2, 2L over 3, right? But now let's look at the frequencies. Because we know that F lambda is equal to V, the speed of sound. So if we find the frequencies, then we can say F0 is V over lambda 0, which is V over 2L. Right. How about the frequency of the first overtone? F1, V over lambda 1. This is V over 2L multiplied by 2. So that's the same thing as twice F0. So now, see the pattern? Here it comes. Next one, frequency of the next overtone. V over lambda 2. And so this must be 3 times V over 2L, which is the same thing as 3F0. So you see what's occurring? The frequencies are related in a very simple way. They're all whole number multiples of the fundamental. The fundamental, twice the fundamental, 3 times the fundamental, 4 times, all integer multiples. Right. So, now that we know that, let's see if we can focus on trying to solve this doggone problem. Because what it's telling us, the problem is, says it's the sound is resonating 2 successive harmonics of 690 hertz and 920 hertz. Great. Let's see how we can work that in. 2 successive harmonics. As is often the case, we have to try to express this in a mathematical way. So here's what we can say. One of these harmonics, whatever it is, we'll call it the nth harmonic. Seems pretty mathy, doesn't it? Nth harmonic is n times F0. Okay? Then it says the next successive harmonic, next successive. Then that must be Fn plus 1, and so this must be n plus 1 times F0. So these 2 harmonics then are successive. Okay. And it tells us then that this is 690 hertz and 920 hertz. Great. Fine. So now we've written down mathematically what it is that the problem tells us. Super. Now what? We have to find the fundamental frequency. Oh boy. The fundamental frequency, that's this thing. You know, it seems like there's all these ends and things. We don't know what the ends are. So how do we take care of this? It's one of these mathematical tricks that you got to really watch. If you take this equation and subtract that one, what do you get? N plus 1 times F0 minus N F0. All I got left is F0. And so subtraction gives us 920 minus 690. This must be 230 hertz. There's the fundamental frequency. How did it get to be so simple? Every once in a while, life deals you some nice, simple things. This is one of them. That's F0. Fine. There's a B part to this problem. This was A. The B part says that what is the speed of sound in the tube? Okay, we're trying to get the speed of sound in the tube. Well, we know what f0 is. It's just 230 hertz. We also know f0 is v over 2L. So how do we find v? Again, simple math. V equals 2L times f0. And since we know what L is 75 centimeters, then when we put this all together, we get, as our speed of sound, 345 meters per second. So we always have to apply our test of reasonability somewhere along the line, and this is no different. We have to say, is that reasonable? Yeah, the speed of sound in air is typically around 340 meters per second, so this is not unusual. It's kind of within the same zone. Maybe it's a little warm that day. That's okay. It'll all work. There it is.